So for this one, we're going for the first order derivative for the numerical differentiations. So before we start, I just introduce another ideas about the timelines. So because later we are going to deal with the points actually. We have the numbers of the points here. We have the forwards, we have the backward, we have the 2 point, we have the 3 point, 4 points formulas for the numerical differentiations. So first of all, I want to introduce here, I have this 5 point here. So let's say I take the center as my reference point here. I just putting as an x here. So this is my x as the center of the point here as a reference. So for the center, for this one, I can just move the points to the left, to the right, or just forward or backwards. So with some increments, so we're calling as a h here. So the h here actually is just stand for the step size. The h, this h we known as a step size. So let's say we want to move to further of the left here. So our x later will become x plus h. So same thing, if let's say we try to move on the backwards over here, so we have the x minus h over here. Yeah, so the same thing, I can just expand all these points to the rest of the points here. So let's say I will just move this point. So this point further to the left here. So now my x here, the point will be further to the, with the h here, the h step size here. So then later I have the, later this one I have the x plus 2h. The same thing, I can just move to the backwards, and this is what I have here. This is the current point. So the current point, I can just move towards the left here. So I have the next point. I also can just move towards to another point. This is the next one, the next 2 points. And the same thing, I can just move to the backwards. So the previous, then you have the previous 2 points. So basically this is about the x here. The same thing for the function, let's say you are dealing with the function values. So this is the current point for the x. So mean the function value will be the fx. So mean that the x plus h, then the function value will become the fx plus h. The same thing for this one. So this is something like we just move from this one to this one. We're just moving for the plus. So because we move forwards, so let's say we're moving to the backwards here. So all the x value will be minus with the x minus h, x minus 2h. So this is somehow like our logic movement, and this is a plus h for each one. Because why are we talking about this? Because later we are going to use for the formulas for the numerical derivative. So actually we have the 6th formula over here. So we have the first 3 formula is 2 point forwards difference, and 2 point backwards difference, and also the 3 points center difference. So why the formula is calling it like something like the 2 points or the 3 points, and also the center or the backward, as well as the later if we have the 5 points something. So because of why? Because of our fx here. Our fx here, this is a plus h, and then you have the fx. Actually, this is the x. This is a minus h. So the same thing, we just draw the timeline here. So let's say this is my x. So I move forward to this one, I have the s plus h, and this is the x minus h. So for this one, we have the x plus h, and this is 0. It's something like we just move forward from x to x plus h. So the same thing for this one, it's an x to x minus h, means that we are dealing with this point, and this point, the function values, and it's moving to the backs. The same thing for this one, the same thing goes for this one. We are taking for the x here is due for the reference. So we take this the x plus h minus this x minus h. So this is somehow like our fx here is just make it as a center, and this is our x minus h, and this is the x plus h. So this is how the ideology about the points, the naming of the formulas. So we have the 6th formula. This is just a 3 formula out of the 6. So next, next we have another 3 formulas here. So this is the 3 point forwards, backwards, and also the 5 point center difference. So what are the difference here? So these are the three formulas we have here. So mainly is we have the 3 point here, meaning that you see this one, this is x plus h, x plus 2h. So meaning that we are moving forward. So that's why we call this is the forward difference. And we have 1, 2, 3 points. So that's why this is the 3 point. Forward, you moving forward, then we call it moving forward difference. So the same thing for the second formulas over here. Is a 3 point? Yes, we have the x minus h, and x minus 2h, the function values. And this is something like we're moving forward from x to minus h, then minus 2h. So this is something like we're going back, we start back. So that's why we're calling as a backwards. The same thing for the last one. We have the 5 point, 1, 2, 3, 4. Why is 4 actually? So actually it's 5 point because we are taking the x over here. So that's why we call 5 points. But the x here is just the centers as a reference, so we just ignore this one. So that's why we take the 5 points. We need the 5 points ideas. And because of this, we have the 6 formulas. We have 3 different at 2 point, 3 points, and 5 points formulas, and the forward difference. And which one is giving us a best approximation of the numerical differentiation? And this is something question very interesting about that. So perhaps the next one, I would like to introduce the ideas how we get a formula, actually the derivative formulas, is based on this one. So by normal, based on our understanding, the first order derivative usually is referring to the slope of the point. So meaning that this is the point that we're going to find this one. So actually it's just if let's say we want to talk about the first order derivative, actually just a slope here. And this is what the true derivative is meaning by the slope, the values. So we can do the approximation by using this point and this point. For example, this one we are using the forward difference formulas. So meaning that we are using only these 2 points to draw for this line, the approximation line. So the best part, if let's say we can get the approximation, is try to get as much as parallel to the true derivative. So why we say to get as much as parallel to the true derivative? Because of what? So when we say it's a parallel, so meaning that the gradients or the slope of these 2 lines are the same. So this is what we call as the best approximation. So try to look back on the next one. So this is something like we're doing for the backward formulas. So the backward formula, we are using this one and this one, the x minus h and the x here. So meaning it's the back here, the backwards. So we draw this using these 2 points, and then we draw the line here. And it's still not very good approximation. It's not very looks like parallel to the two derivative, and this is not very good. The same thing we can use for the 3 point center difference formulas. Yeah, so we're using this point, the x minus h, and this is x plus h. Your x here, actually you want to approximate the x here, the values. So you just draw the line here, and then you get the first order approximation for the first order derivative. So right now we're here. So on which one is the best approximation? Of course, we have the 3 different formula. We're taking about 3 point and the 2 point. And which one is the best and why? For this case, I can say the center difference will be a best formula. So why I'm saying this is the best approximation, because of what? Because this is almost parallel. The approximation line is almost parallel to the true derivative, and this is why we say the center difference formula is better. Of course, we have another issue about this. How about the gap for the step size? It is the step size getting smaller is better. Yes, if the step size is smaller, you will get a better approximation. Besides that, you're using the center difference formula.